Let us continue our discussion of section 1.1, numbers and sequences. Last time we discussed rational numbers and irrational numbers. We proved that square root of 2 is irrational using the well-ordering property. Let us go over this proof once again. Step 1. Assume to the contrary that square root of 2 is rational, which means square root of 2 is equal to a divided by b, where both a and b are integers. Moreover, b is not equal to 0. As we discussed, without loss of generality, we can assume that a and b are positive integers. Indeed, if both a and b are negative, we can multiply top and bottom by -1, and as the result, top and bottom become positive. Here's what we do next. If we multiply the left-hand side and the right-hand side by b, we get this. And now let us consider the following set. Set S consists of all integers k such that both k and k times square root of 2 are positive integers. Question is it true that S is non-empty? The answer is yes. Here is why. Please take a look at this and at this. Note that since a is a positive integer and since a is equal to b times square root of 2, b times square root of 2 is also a positive integer. According to 2, b is a positive integer. So both b and b times square root of 2 are positive integers. Therefore, this set S has at least one element, b. b is an element of S because both b and b times square root of 2 are positive integers by 2 and 3. Since S is non-empty and since S is a set of positive integers, we can apply the well-ordering property. By the well-ordering property, S has a smallest element. Let us denote it by a lowercase s. Clearly, since a lowercase s is an element from S, both a lowercase s and lowercase s times square root of 2 are positive integers by this. Here is what we do next. Let us consider the following new number. W is equal to s times square root of 2 minus s. Let us show that number 1, W, is from this set again, and let us also show that W is smaller than S. Obviously, this will give us a contradiction because we know that lowercase s is a smallest element from S. So, how do we show that W is from S? First of all, let us show that W is a positive integer. W is an integer because both S and S times square root of 2 here are integers by 4. Since W is the difference of these two integers, W is an integer. Moreover, W is a positive integer because W by this is S times square root of 2 minus S. We get the following: S times square root of 2 minus 1. But S is positive by 4. Square root of 2 minus 1 is positive. Therefore, W is equal to positive times positive, which means W is positive. So, by 1, W is positive integer. Number 2, let us show that W times square root of 2 is also a positive integer. First of all, W times is positive because W is positive by 1 and square root of 2 is positive. So positive times positive is positive. Now let us show that W times square root of 2 is an integer. Here's why. I'll replace W by S times square root of 2 minus S, thanks to this. And then expand parentheses. S times square root of 2 times square root of 2 is 2S. S times square root of 2 is this. And now know that since S and S times square root of 2 are integers by 4, 2S minus S times square root of 2 is an integer. Conclusion: W times square root of 2 is positive integer. Lastly, let us show that W is smaller than S. W by this is S times square root of 2 minus S. Let us factor out S. Note that since square root of 2 minus 1 is lesser than 1, S times square root of 2 minus 1 is lesser than S. And now let us put pieces together. From 1 and 2, it follows that W is an element of S. But by 3, W is smaller than S. This contradicts the choice of S as the smallest integer in S. So, we assumed that square root of 2 is irrational. We got a contradiction. Therefore, square root of 2 is not rational, means irrational. All right. But now, guys, let us talk a little bit in general about this course. One of the goals in this course is to help you develop the ability to prove theorems. I've never said that after this course you will know how to prove theorems. It's a very hard process, but you will get some understanding about what is a proof. One of the ways of learning how to prove theorems is to try to tweak the existing proof. Try to modify, try to generalize, try to simplify, and so on and so forth. So, first of all, let us try to see better a big picture here. Please take a look at remark number 1. Here's a short version of the proof above. Step 1, assume that square root of 2 is irrational. Step 2. Let s be the smallest positive integer whose product with square root of 2 is an integer. Of course, big question is, does such an s exist? Indeed, if we assume that square root of 2 is rational, such s exists by what is written here and by the well-ordering property. So we skip lots of steps. We come up with this relatively short sentence that allows us to see picture clearer, but we drop lots of details. After that, consider this. Note that since square root of 2 minus 1 is lesser than 1, s times square root of 2 minus 1 is smaller than s. And also note that this number times square root of 2 is an integer again. This is exactly what we show here. We got a contradiction. So this is a trade-off. We skip lots of details, but it helps us to see a bigger picture better. Lastly, remark 2. Another version of the proof above can be found in Appendix 1. This version is taken from the textbook. However, this version is a little bit longer than version number 1. Let us compare. So please take a look. Part number 1 is same up to this formula. It's totally same, it's just a copy. However, in the textbook, instead of k here, the author decided to put k times square root of 2. Here is what we do next. As before, we show that s is non-empty. Why s is non-empty? Because b and b times square root of 2 are positive integers by 2 and 3. So b times square root of 2 is a member of s. Compare with the original version. Here we have b. Here we have b times square root of 2. Because in version number 1, elements of s are k's. In version number 2, elements of s are k times square root of 2. So over here, instead of b, we put b times square root of 2. Here's what we do next. By the well-ordering property, s has a smallest element. Say s is equal to t times square root of 2. Compare. Over here, we denote smallest element by s. But in version number 2, each element has form k times square root of 2. Therefore, s is equal to t times square root of 2. This portion is same. W is s times square root of 2 minus s. Next, as before, in order to get a contradiction, we will show that number 1, w is from s, and number 2, w is smaller than s. How to show that w is from s? Number 1, observe that s times square root of 2 is positive integer. Obviously, because s is t times square root of 2, done. Square root of 2 times square root of 2 is 2. Since 2 is positive and t is positive, it's written t is positive. 2 times t is positive. Next, w is an integer because s times square root of 2 is an integer by 1. S is an integer by 4. It's written as is an integer. And w is the difference of these integers. And then, as before, similar to this, we show that w is positive. So by 2, w is positive integer. W is an element of S. In order to show that W is from S, we have to show that W, which is this, can be written as integer times square root of 2. In order to show that, let us replace S by T times square root of 2, factor out square root of 2, and then, since s minus t is a positive integer, w can be written as positive integer times square root of 2. By the way, here's another thing. It is pretty clear that s minus t is an integer. Question is why s minus t is positive integer? It's all because s minus t is w divided by square root of 2, which is positive. Lastly, as before, we show that w is lesser than s, and we get a contradiction. So folks, this version, if we show all details, is longer than version number 1. Here's another thing. Let us consider another version of version number 2. Observe that in this expression, we can actually replace s by t times square root of 2. This gives us a shorter approach. So here's what we do. We copy portion number 1. We copy portion number 2, same as before. It's just a copy. We also copy this. However, let us modify what is written here. By the well-ordering property, S has a smallest element, say, and instead of writing down S is equal to T square root of 2, say S square root of 2. It's totally obvious that this is an element of S because it is of this form. By the well-ordering property, S has the smallest element, say S square root of 2. Now, according to what is written here, both S and S square root of 2 are positive integers. Now, instead of considering W is equal to S square root of 2 minus S, note that if you replace S here and here by T square root of 2, we'll get the following. T square root of 2 times square root of 2 minus T square root of 2. But T square root of 2 times square root of 2 is 2T. It's exactly what we do here. Note that over here, T is gone. We have just S. So let us consider the following W. W is 2S minus S square root of 2. And then, number 1, W is integer because this is an integer and this is an integer. Moreover, it's a positive integer because if we factor out s, we get s times 2 minus square root of 2, which is positive. W times square root of 2 is positive because W is positive. Moreover, it's an integer because if we replace W by this expression done and expand parentheses, we get this. But by 4, square root of 2 times s is integer. S is integer, therefore this is an integer. And lastly, W. Now, instead of W is lesser than S, we have to put W is lesser than S times square root of 2, because S smallest element is of the form S square root of 2. But it's easy to show that W is lesser than S square root of 2. Just take a look at this. W is this, factor out S. Since 2 minus square root of 2 is lesser than 1, the whole thing is lesser than S. And since square root of 2 is greater than 1, S is lesser than S times square root of 2. Note that in order to come up with this proof, we just replace S over here and over here by T times square root of 2 and get rid of T. As the result, the proof becomes a little bit shorter. Lastly, please compare this version with this one. The difference between these two versions is the following. Question is, why consider this W? Maybe it is possible to replace 2s minus s times square root of 2 simply by the very first expression, s times square root of 2 minus s. And indeed, this works. So we copy the whole portion over here and replace this by this. This is the last version. If you take a look at the rest, basically the rest is a copy of what is written here. And we are completely done. So once again, to reiterate, the default approach is version 1. But in Appendix 1, we just look at what happens if we tweak a little bit this proof. Next, remark 3. Is it possible to use this approach to prove that, say, square root of 3 is an irrational number? Turns out that the answer is yes. We just replace square root of 2 by square root of 3 everywhere. It's written in Appendix 2. Let us compare line by line. Of course, we replace square root of 2 by square root of 3 in the original statement. We replace square root of 2 by square root of 3 here, 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 and here. Done. We replace square root of 2 by square root of 3 here and here. Done. And then we replace square root of 2 by square root of 3 everywhere over here. One can easily see that despite the fact that we replaced square root of 2 by square root of 3, every line in this proof is correct. However, we have to do some adjustments if we want to prove that square root of 5 is irrational. Namely, instead of w is equal to s square root of 5 minus s, we should put w is s square root of 5 minus 2s. Here is why. Note that in 3, we have to show that w is lesser than s. If instead of s square root of 5 minus 2s, we just copy this with 5 instead of 2, we will not be able to prove this inequality, because s square root of 5 minus s is not lesser than s, because square root of 5 minus 1 is not lesser than 1. So once again, in order to make this happen, we modify this expression twice. We replace 2 by 5, and we replace minus s by minus 2s. Folks, any questions here?
I have a question about why we have to use s. Could we just replace s with 1?
Well, if you put here minus 1, a bunch of things will be destroyed. Let me go back first to this. So, if instead of s square root of 2 minus s, we put s square root of 2 minus 1, to begin this will not work, because s square root of 2 minus 1 is not necessarily lesser than s. Think about this. Okay. S times square root of 2 minus 1, if you move 1 to the right and s to the left, we'll get the following. S square root of 2 minus s should be lesser than 1. It's not true. Think about s as about 10. 10 times square root of 2 minus 1 is not lesser than 10. Also, 2 will not work. Here's why. If instead of s here we have 1, after expanding parentheses, we'll get the following. S times square root of 2 times square root of 2 is still 2s. But then, if instead of s here we have 1, after we expand parentheses over here, we'll get square root of 2. But square root of 2 is not an integer. It's a rational number according to our assumption. So we'll get integer minus a rational number, which is not necessarily an integer. Other questions?
Yeah, so for when you're making w, say
Yes.
you want to do like root 11 or like root 7, would you have to raise, so like w equal, would you have to raise the value in the minus 2s? Would you have to make it like a 3s or a 4s?
Exactly.
Okay.
So in order to come up with this number, we consider the so-called floor function of this. So compare. Floor of square root of 2 is 1. So we put 1 in front of s. Floor of square root of 5 is 2. We put here 2. If instead of square root of 5 you have, for example, square root of 10, you put here 3, because floor of square root of 10 is 3. Does this answer your question?
Yeah, thank you.
Other questions?
I have a question. Sorry,
Yes.
what do you mean by floor?
Floor function is the following. Floor of x is the largest integer that does not exceed x. For example, floor of 1.1 is 1. Floor of 2.9 is 2.
So for square root of 10, you said it would be minus 3s.
Yes, because square root of 10 is between 3 and 4. So floor of square root of 10 is 3. 3 is the biggest integer that does not exceed square root of 10. Does this make sense?
Yes, thank you.
Now, guys, let us try to prove that cubic root of 2 is irrational. Now the proof is even harder. Instead of considering S that consists of integers k, such that both k and k times cubic root of 2 are positive integers, we consider this S. Let us consider this set S that consists of all positive integers such that k and k times cubic root of 2 and k times cubic root of 4 are positive integers. Please take a look at example 3. So, as before, assume to the contrary that cubic root of 2 is a rational number. Without loss of generality, we can assume that a and b are positive integers. What is written here can be rewritten as a is equal to b times cubic root of 2. Now let us consider this set S. As before, let us show that S is non-empty. Now it's a little bit harder to prove. By 2 and 3, b and b times cubic root of 2 are positive integers. But we have one more condition. So here's what we do. If we square both sides here, we get this. Since a is an integer, a square is an integer. Since a left-hand side is equal to a right-hand side, b squared times cubic root of 4 is an integer. Lastly, since b is a positive integer, b squared is a positive integer. Since b times cubic root of 2 is a positive integer, b squared times cubic root of 2 is a positive integer. So this is a positive integer, this is a positive integer, this is a positive integer. All three are positive integers. Therefore, set S is non-empty. Folks, any questions here?
Why are we looking at b squared in the first place?
Well, according to what is written over here and over here, b and b times cubic root of 2 are positive integers. But this does not necessarily mean that b times cubic root of 4 will be an integer. We say the following: since b squared cubic root of 2, b squared cubic root of 4 are positive integers, this set is non-empty. And this is a positive integer because we square both sides. Done. Since a square is a positive integer and a square is equal to this is a positive integer as well. And now, since in front of cubic root of 4 we have b squared, we have to put b squared here and here, because in this we have k, k, and k. Does this make sense?
Yes, thank you.
Now, this expression is pretty much same as before. Just we replace square root of 2 by cubic root of 2. Now see what happens next. First we show that w, this w is positive integer. It is an integer because s is an integer by 4, and s cubic root of 2 is an integer by 4. So w is integer minus integer, therefore w is an integer. Moreover, w is a positive integer because this is positive and s is positive. Now you may wonder, why in the world over here, in addition to k and k times cubic root of 2, we need this? Well, here's why. Please take a look at 2. Let us show that w times cubic root of 2 is a positive integer. Well, w times cubic root of 2 is positive because both w and cubic root of 2 are positive numbers. But why this is an integer? Here's why. So let us start with w times cubic root of 2. W is this, so we replace w by this expression. Now let us expand parentheses. Done. Observe that cubic root of 2 times cubic root of 2 is cubic root of 4. Therefore, if we do not have this portion, we will not be able to show that the whole thing is an integer. We need both this and this in order to prove that the difference is an integer number. But this is not all. Compare with this proof. In 2, we just show that w times square root of 2 is a positive integer. Since over here we have 3 conditions, in addition, we have to show that w times cubic root of 4 is a positive integer. Well, it's easy to show that it's positive, but why w times cubic root of 4 is an integer? Well, we replace w by this expression first. We expand parentheses. Observe that cubic root of 2 times cubic root of 4 is 2. Since s is an integer and 2 is an integer, 2s is an integer. And lastly, by this, s times cubic root of 4 is an integer. Integer minus integer is integer, so this is an integer. And lastly, it is easy to show that w is lesser than s. Over here, we got a contradiction. W is from our set S. W is smaller than lowercase s, which gives us a contradiction. Very last remark. Question is it possible to adapt the proof above in order to show that, say, pi is irrational number? No, guys, it is significantly harder to prove that pi or, say, e are irrational numbers. And here's why. Let us take a look at this part of the proof. If we replace square root of 2 by pi, Over here, we will get W pi. Over here, we will get S pi minus S. After expanding parentheses, we'll get S pi square minus S pi. But this is not an integer because pi square is not an integer. Over here, this expression is an integer because square root of 2 times square root of 2 is 2, which is an integer. Square root of 2 square is an integer. Pi square is not an integer. This is one of the reasons why we can't easily adapt the above proof to this new situation. In Appendix 3 and in Appendix 4, I show you how to prove that E is irrational and pi is irrational. By the way, this proof is just a sketch. Complete proof is pretty long. We are done with part number 1. Part 2, sequences. Stated formally, an infinite sequence, or more simply, a sequence, is an unending succession of numbers called terms. Here are examples of infinite sequences. 0, 0, 0, and so on. It's a sequence. 1, 2, 3, 4, 5. We can use expressions A1, A2, A3, and so on. Sometimes as subscripts. We use negative numbers. B subscript negative 2, B subscript negative 1, B0, B1, B2, and so on. Here is 3 examples of famous sequences. Prime numbers, Fibonacci numbers, Catalan numbers. Now, let us consider a rigorous definition of a sequence. A sequence is a function whose domain is a set of integers. Here's why. Please take a look at this example. An is equal to n. Domain is subscripts. For each input, we have the corresponding output. A1 is 1, A2 is 2, A3 is 3. Please take a look at this. Inputs are 1, 2, 3, and so on. Outputs 1 if n is equal to 1, 1/2 if n is equal to 2, 1/4 if n is equal to 3, and so on. Here's another example. An is equal to -1 to n plus 1 times n over 2n plus 1. This portion allows us to alternate signs. 1/3, -2/5, 3/7, and so on. Okay, 2 more classical sequences. Arithmetic sequence means the following. AK is equal to AK minus 1 plus D. Explicitly, AN is equal to A0 plus DN. For example, the sequence 5, 11, 17, 23, 29, and so on is an arithmetic sequence. Here, the initial term is equal to 5, D is equal to 6, because in order to jump to the next term, we add same number, 6, to the previous term. 5 plus 6, 11, 11 plus 6, 17, 17 plus 6, 23, 23 plus 6, 29, and so on. So D is a fixed number. In order to come up with an arithmetic sequence, we need two numbers, A0 and D. Similarly, geometric sequence. Instead of plus here, we put times. AK is equal to R times AK minus 1. Next term is R times previous term. Explicit formula. AN is equal to A0 R to nth power. Here's an example of geometric sequence. 6, 12, 24, and so on. So once again, guys, how do we recognize arithmetic sequence? If we see that the difference of any two consecutive terms is a fixed number, this is an arithmetic sequence. If we see that the quotient of two consecutive terms is a fixed number, this is a geometric sequence. Over here, A0 is 6, R is equal to 2, because 12 divided by 6 is 2, 24 divided by 12 is 2, and so on. Lastly, this portion is about finding terms of sequences. So, formula is given, AN is equal to 5, no matter what is n. Write the first 5 terms. It's pretty obvious. A1 is 5, A2 is 5, A3 is 5, A4 is 5, A5 is 5. Here's another example. AN is equal to n. Then A1 is 1, A2 is 2, and so on. A5 is 5. AN is 1 over n. And now we start with 4, because it's written n is greater or equal to 4. The first 5 terms are A4 is 1 over 4, A5 is 1 over 5, and so on. A8 is 1 over 8. As I said, we can start even with negative numbers. AN is square root of n plus 5, where n is greater or equal to negative 2. If n is negative 2, the expression under the square root is 3. So a subscript negative 2 is square root of 3. A subscript negative 1 is square root of 4, and so on. A subscript 2 is square root of 7. It's just a more complicated expression, 7 plus n squared over 10 minus n. We just plug in 1, 2, 3, 4, and 5 instead of n, and we get these terms. Now, in order to generate alternating signs, we multiply our expression by -1 either to nth power or to n plus first power. Here is the difference. If n is greater or equal to 1, over here, term number 1 will be negative, because -1 to first power is -1. Over here, term number 1 will be positive, because -1 squared is +1. So here we start with negative term, here we start with positive term. Lastly, if a formula is given, it is not so hard to find terms of our sequence. However, the opposite question is significantly more complicated. Suppose we have few initial terms. Find an explicit formula. Of course, we start with relatively simple examples. 1, 1, 1, and so on. It is not that hard to come up with a formula. An is equal to 1. Or over here, 1, 2, 3, 4, 5, and so on. An is equal to n. Just be careful. Here, find an explicit formula for the sequence of the form A1, A2, A3, but we start with 3. So An is no longer n. An is n plus 2, where n is greater or equal to 1. Greater or equal to 1 because it is said we have to start with A1. So once again, since we have to start with A1, we have to adjust this expression. Instead of An is equal to n, which gives us this sequence, we should put An is equal to n plus 2, where n is greater or equal to 1. Over here, 1 over 7, 1 over 8, and so on. An is equal to 1 over n plus 6, where n is greater or equal to 1. This example is harder. We have to recognize the pattern. 4, 9, 16, these are squares. Squares of consecutive integers. But again, we do not put inside the cubic root n square. Since here 4, and we start with A1, An is cubic root of n plus 1 square. This example, we have alternating signs, and we start with a negative term. So we multiply the whole construction by -1 to nth power. To the contrast, if we start with a positive term, we rise -1 to the power n plus 1. We are pretty much done for today. Next time, we will discuss this example. Guys, as I said, this type of problems is significantly harder than the problem of finding terms if a formula is given, because it's all about pattern recognition, and often it's hard to recognize the pattern. So please don't read the solutions. Try to do these examples without any hint.